On July 29, 2025, off the coast of Russia's Kamchatka Peninsula, a section of ocean floor roughly 400 kilometers long suddenly lifted upward by as much as 13 feet in a matter of seconds. That single violent motion sent a wall of energy racing across the entire Pacific Ocean. And by pure chance, a NASA satellite happened to be flying directly overhead at almost exactly the right moment to see it happen. What it captured has just been published. It's spreading fast through the scientific community right now, and it is forcing researchers to rethink something they thought they already understood. Tsunamis, it turns out, do not move the way textbooks have described them for decades. Let's start with the number that set all of this in motion. Magnitude 8.8. That's how strong the earthquake was that ruptured the Kuril-Kamchatka subduction zone that day, making it the most powerful earthquake anywhere on Earth since the catastrophic 2011 Tohoku disaster in Japan. The rupture along the fault stretched roughly 250 miles, and in places, the seafloor was thrust upward with enough force to displace an entire column of ocean water above it. That displacement is what creates a tsunami, not a single wave, but a genuine deformation of the ocean itself, spreading outward in every direction at jet aircraft speed. Here's the part of this story that almost nobody outside the research community has actually seen. Explained clearly, and it's the part that matters most. For 70 years, scientists have tracked tsunamis using a network of seafloor sensors called DART buoys, deep ocean assessment and reporting stations that detect pressure changes as a wave passes directly above them. That system works, but it has one major limitation. A DART buoy can only tell you what the wave looked like at one single point in the ocean, the exact spot where the buoy happens to sit. It cannot show you the shape of the wave across the wider ocean. It's like trying to understand an entire storm system using only a handful of scattered weather stations. You get useful data points, but you're missing the full picture entirely. This time was different because NASA and the French space agency CNES had a satellite called SWOT, short for surface water and ocean topography, passing over the exact stretch of ocean where the tsunami was spreading, roughly 70 minutes after the earthquake struck. SWOT wasn't even built for this. It was designed primarily to map rivers, lakes, and ocean surface features here on Earth with extraordinary precision. But because of an almost accidental alignment of timing and orbit, it became the first satellite in history to capture a high-resolution, wide-area view of a major subduction zone tsunami as it actually moved across open ocean. If you want to understand exactly what scientists found buried in that data and why it's changing how tsunami warning systems may work in the future, that's exactly what we're breaking down today. I'm the host here at Today Latest Analysis, and we go straight to the actual published research on stories like this, not just the dramatic headlines. Subscribe now, because science stories like this one are exactly what we cover the moment the data becomes public. Now let's start from the beginning, because to understand why this discovery matters, you first need to understand what scientists expected to see, and why what they actually found was so different. For decades, the mental model most people have of a tsunami, and honestly the model many simplified forecasting tools have used too, is something close to a single clean ring of energy expanding outward from the earthquake's epicenter, like a stone dropped in a pond, just on a planetary scale. It's a useful simplification. It's also, according to this new data, not what actually happens. When researchers pulled the SWOT satellite's readings of sea surface height across the tsunami's path, what they found was not a single clean expanding ring at all. Instead, they saw a genuinely complex wave field, energy spreading outward, yes, but also scattering, dispersing, and interacting with itself as it crossed different sections of ocean. Some of that scattering came from the shape of the seafloor beneath the waves, some from the specific geometry of how the fault ruptured, and some from wave interactions that simply hadn't been observed directly at this scale before. The wave that reached Japan wasn't a simple pulse. It was a complicated, layered structure that traditional single-point sensors were never capable of revealing. Here's the number that makes this tangible. As the tsunami's leading edge passed east of Japan, SWOT measured a broad crest just over 45 centimeters, about 1.5 feet above normal sea level, out in the deep open ocean. That might not sound dramatic. In open water, 1.5 feet of extra height spread across dozens of miles of ocean is barely something a ship would notice rocking through. But that same energy, when it reaches shallow coastal water and gets compressed and forced upward by the seafloor rising toward shore, is exactly the mechanism that turns an unnoticeable open ocean swell into a wall of water capable of destroying a coastal town. Understanding the true shape and structure of that wave while it's still far out at sea is the difference between an accurate warning and a rough guess. Now here's the second layer of this story, the part that explains why this data is genuinely valuable beyond just being visually impressive. Scientists didn't only use the satellite images to look at the wave. They combined the SWOT data with readings from 3 separate dart buoy stations positioned near the earthquake's source, and used that combination to work backward and reconstruct the earthquake itself, a technique called source inversion. By comparing how the tsunami actually formed and spread against the seafloor deformation models, researchers were able to estimate with much greater confidence exactly how the fault ruptured, how far it extended, and how much the seafloor moved in different sections along that 250-mile rupture zone. In other words, this satellite designed to map rivers and lakes ended up helping scientists reconstruct the anatomy of one of the most powerful earthquakes of the century, almost as a byproduct of watching the wave it created. There's a specific comparison in the published research that deserves attention because it's really the headline finding underneath all of this. Researchers directly compared what SWOT actually observed against NOAA's operational tsunami forecast model, the same type of model used in real time to issue warnings to coastal communities across the Pacific. The satellite data confirmed that the model's predicted wave heights and arrival times lined up closely with what genuinely happened. That's an enormously reassuring result on one level. It means the forecasting tools currently protecting coastal populations are fundamentally sound, but it's also exactly why the added complexity SWOT revealed matters so much. If the underlying wave structure is more intricate than the simplified models assume, even when those models get the big picture right, there's now a clear evidence-based pathway to make them sharper, and sharper models mean faster, more precise warnings, especially for the specific sections of coastline that end up facing the worst of a given tsunami rather than a generalized regional estimate. To understand why this region produces earthquakes and tsunamis this powerful in the first place, it helps to look back at its history. The Kuril-Kamchatka subduction zone has a long, well-documented track record of generating devastating tsunamis. A massive earthquake in this same region back in 1952 triggered a Pacific-wide tsunami that caused serious damage and loss of life across the ocean, and that event was a direct catalyst for building the coordinated international tsunami warning system that still operates today. The same network of dart buoys and regional warning centers this new satellite data is now helping to improve. The 2025 Kamchatka earthquake tested that system again, more than 70 years later, and while the DART network and NOAA's warning process performed well, catching the threat and issuing appropriate alerts across the Pacific, it also revealed how much additional insight becomes available when a wide-area satellite view is added into the mix, rather than relying purely on scattered point sensors. This naturally raises the question a lot of people ask the moment they hear a headline like this one. Does this discovery mean tsunamis are becoming more dangerous, or that something unusual is happening in the Pacific right now? Here's the direct, honest answer. No. This isn't a story about increased risk. It's a story about increased visibility. The physics of how earthquakes generate tsunamis hasn't changed. What's changed is our ability to actually see the full shape of a tsunami wave as it crosses the ocean, instead of inferring it indirectly from a handful of scattered buoy readings. That's a genuine scientific advance, not a warning sign. The Kamchatka event was a powerful, historically significant earthquake, but it did not represent some new or escalating category of danger. What it represented was, for the first time, the right satellite being in the right place at the right satellite, being in the right place at the right moment to capture something researchers had only ever been able to model in theory. That distinction matters, because stories involving NASA, satellites, and words like tsunami tend to get pulled towards sensationalism online very quickly. The actual finding here isn't dramatic in the disaster movie sense. It's dramatic in the way real scientific breakthroughs usually are, quiet, technical, and enormously useful, precisely because it improves the tools protecting millions of people living along Pacific coastlines, rather than revealing some previously hidden threat. So here's what this actually means for the future, and why it's worth paying attention to, even if you don't live anywhere near the Pacific Ocean. SWOT wasn't purpose-built as a tsunami detection satellite, it just happened to be positioned correctly during this specific event. But this result has demonstrated, with real data rather than simulation, that satellite altimetry, the technique of measuring surface height from orbit, can meaningfully improve tsunami source modeling and potentially validate or refine warning forecasts in near real time. Scientists are now actively discussing what a purpose-built constellation of similar satellites could offer: wide, continuous coverage of ocean surface height across entire ocean basins, rather than relying on the chance that a single satellite happens to pass overhead at the right moment during the next major earthquake. For coastal communities in places like Japan, Chile, Indonesia, the Philippines, and the US Pacific Northwest, all of which sit near active subduction zones capable of producing tsunamis on this scale, that kind of continuous space-based monitoring could eventually mean the difference between a generalized regional warning and a precise, localized alert with a clearer picture of exactly which stretches of coastline face the greatest danger. It's also worth remembering just how much of this result came down to sheer timing. SWOT only launched in 2022. Researchers had spent roughly 2 years using its data mostly to study smaller-scale ocean features, eddies, currents, subtle surface patterns, useful science, but nothing on the scale of a Pacific-wide megatsunami. Then, on July 29, 2025, one of the most powerful earthquakes of the century happened to rupture in a location that placed the resulting tsunami directly beneath the satellite's orbital path, within about 70 minutes of the initial rupture. That is an extraordinarily narrow window. A slightly different orbit, a slightly different earthquake location, and this entire data set simply wouldn't exist. Scientists are now working from the assumption that they got lucky once, and building the case for making sure the next observation doesn't have to depend on luck at all. There's one more layer to this story worth understanding, because it explains exactly how a satellite designed for rivers and lakes ended up producing data precise enough to reconstruct an ocean-crossing megatsunami. SWOT doesn't measure the ocean the way older altimetry satellites did, tracking a single narrow line directly beneath the spacecraft as it orbits. Instead, it uses a technology called Ka-band radar interferometry, which allows it to sweep a wide swath of ocean surface, roughly 75 miles across on either side of its ground track, all at once, measuring sea surface height with a precision down to just a few centimeters. That's the technical leap that made this discovery possible. Older satellite altimeters could only have captured a thin sliver of the tsunami's path, essentially the same single-point limitation as a dart buoy, just from orbit instead of the seafloor. SWOT's wide swath meant it captured the actual two-dimensional shape of the wave field as it crossed that stretch of the Pacific. The scattering, the dispersion, the interaction patterns, all of it visible at once in a single pass, rather than reconstructed after the fact from scattered individual readings. That is the specific engineering breakthrough that turned an ordinary orbital pass into the first genuine snapshot of a subduction zone, tsunami's true shape. Scientists involved in the study were careful to frame this as validation layered on top of discovery, not a replacement for the systems already in place. The Dart Buoy Network and NOAA's forecasting models did their job during the actual event, issuing appropriate warnings and advisories across the Pacific within minutes of the earthquake, exactly as they're designed to. What SWOT added wasn't a correction to that response. It was a far richer dataset sitting alongside it, one that future researchers can use to stress test and refine the underlying wave physics those forecasting models rely on. Think of it less like discovering the existing warning system was wrong, and more like finally getting a high-definition camera pointed at an event that, until now, scientists had only ever been able to reconstruct indirectly, piecing together a handful of data points scattered across thousands of miles of open ocean. The research behind all of this was published in the Seismic Record, a peer-reviewed journal from the Seismological Society of America, giving the scientific community a fully documented source-inverted model of exactly how the Kamchatka earthquake ruptured and how the resulting tsunami actually propagated across the Pacific, verified against real satellite measurements rather than simulation alone. That combination, a real megaquake, a satellite in the right place at the right time, and a direct comparison against operational forecasting models, is what makes this particular event such a valuable case study for the future of tsunami science. I'll bring you the next major update the moment researchers publish findings from any similar satellite pass during a future event, because this is very likely the first entry in what becomes a much larger body of research. If you want science, stories broken down accurately, without the exaggeration that usually comes with headlines involving satellites and tsunamis, that's exactly what we do here every time research like this gets published. Drop a comment and let me know if you live along a Pacific coastline, or if this is the first time you're hearing about how satellites like SWOT actually work. Subscribe so you don't miss the next breakdown. Share this with anyone who'd find it genuinely fascinating rather than just alarming, and I'll see you in the next one.